Hi, welcome back. We're on 7.3. This is thermal inversions. So some big ideas that you should take away from this video are knowing that during a thermal inversion, the normal temperature gradient in the atmosphere is altered. That means that before going into this video, you should have a pretty good understanding of how a normal temperature gradient works within the troposphere as we move up into the stratosphere. And then you should also understand that thermal inversion traps pollution close to the ground, especially smog and particulates. So you should have an understanding of what generally causes smog formation in the troposphere. So what are our learning objectives? To be able to describe thermal inversions and describe thermal inversions' relationship with pollution, which is why we care about them so much. Now, it's important to note that a thermal inversion is not anthropogenic. A thermal inversion is a weather phenomena that is unrelated to anything that humans do. The impact that humans have on thermal inversions is the pollution aspect, and we'll kind of talk about those. So let's look at how a thermal inversion differs from what we consider normal conditions. So look at the temperature gradient that we're seeing here. This is common to what we would see in the troposphere, that the air closer to the surface tends to be warmer. And because hot air wants to rise, it will move towards the stratosphere. But as it moves towards the stratosphere, there's less pressure placed on it. So the air molecules themselves want to spread out further apart, and that actually ends up cooling the air. So the higher up we go in the troposphere, the colder it is. And then if you recall from learning about adiabatic heating and cooling, this cold air will be very dense and it will want to fall. And as it falls, it will begin to heat again and the whole process will start again. Now, what's really nice about these normal conditions is that as this warm air rises, these molecules are much more condensed, but when they rise, they sort of separate. And what this really does is anything that was sitting in that area closest to the surface of the earth, any pollutants or particulates that are sitting in that air are going to rise up and disperse. So they're not going to sit in this one spot. They're not going to sit right in the middle of the city. And so we really largely depend on that. So during a thermal inversion, though, this is where it becomes problematic. We actually see cold air that gets trapped under a layer of hot air. And that hot air is going to be called the inversion layer. Now, because cool air is much denser and it wants to sink, it doesn't really have the ability to pass through this hot air inversion layer. So you get this cold air that sinks, that's really dense, and that just sits in all of those pollutants that we've been emitting. So whether that be particulates or emissions from combustion of fossil fuels, it all just sort of sits there. And we really sort of learned about this during our London smog activity. We learned about how air got trapped, it wasn't able to move, and in return, a heavy amount of pollutants ended up sitting in that area. Gotta plug in. So this is largely problematic for collecting large amounts of pollutants in one area really close to the city. And this is really problematic for things like photochemical smog, because we know the precursor to things like photochemical smog are nitrogen oxide. This allows for an abundance of nitrogen oxide and in turn, a large collection of photochemical smog. So what causes this? What causes this sort of phenomena to occur? Well, I think if you kind of think about it, like why might we see this trapping of cold air under a layer of warm air? You might be able to think about it. So really, anytime the air near the ground is rapidly losing heat, we're going to see an inversion layer form. So if we have relatively warm air, but something drastically shifts that causes the layer underneath that to cool very quickly, we're going to create this inversion layer. So it could be as simple as when the air near the ground rapidly loses heat on a very clear night, the ground will become cold very quickly, whereas the air above it will retain heat, and you'll create an inversion layer. Really common in coastal areas, so we actually see this a lot here living in Orange County, but we have upwelling of cold water that comes near the surface. And if we have a big onshore breeze, that onshore breeze can come up. It can chill the air closest to the surface, but leave very warm air above it. That's going to leave that inversion layer happening. Also really common in areas that form between mountain ranges and have valleys. Cool mountain air can flow from the tops of the peaks of the mountains into valleys and push cold air underneath that warm air since it's more dense. That can create an inversion. Or if we have a lot of snow happening. So if it's a relatively warm day, but all of a sudden it starts snowing, once snow hits the ground, it's much colder. That white color will reflect all of the heat coming in, and so the air above it will become very warm, whereas the cold snow on the ground will remain relatively cold. So there's a bunch of different ways that this can happen, but the big idea here is that those are non-anthropogenic causes, right? Whereas trapping pollutants in between an inversion layer and the ground, that problem is anthropogenic. So other things that can influence thermal inversions, things like valleys. If you live in a valley, you're far more prone to an inversion layer coming, especially if you're nearby mountain ranges and the cooler air of those mountain ranges, it's making its way down into those valleys. If you live near a coast or where prevailing winds are, this is what we see here in the Orange County area, those onshore breezes coming in and cooling our air very quickly and trapping pollutants in that inversion layer. And it's generally more characteristic. Pollution will be more intensified in areas that more pollution exists. So large cities or areas of high industrialization, lots of vehicles. Thermal inversions really aren't problematic for people. The problem is the pollution that exists that gets trapped in that inversion layer, just like you saw in the London smog example. That's where it's largely problematic. Thermal inversions themselves, minus the pollution, really don't have any negative impacts and will clear up on their own. There's nothing that needs to be done. It's just a weather phenomena. Now, something that you should think about, just because we live here, is the LA smog, the photochemical smog that we always see over LA, and we actually get a pretty good view of this from Sage. If you look over to LA in the distance, you'll often see that really dense, thick, kind of brownish photochemical smog sitting over there. A lot of this is due to thermal inversions. So these onshore breezes or these prevailing winds coming off the ocean is bringing in this really cool marine air, which is going to take that warmer air, which is sitting in those cities, of course, because industrialized areas and big cities tend to just be warmer in themselves, more activity, more pollution, and it's going to create a pretty strong a layer of photochemical smog and as a result of a thermal inversion. These things that are kind of shifting upward, this is as a result of the Santa Ana winds. So the Santa Ana winds are actually an example of what we call a high pressure system. So again, similar to what you learned about in the London fog example. The high pressure systems basically mean that the pressure downward is greater. So it's forcing everything downward even more so than usual, and that strong Santa Ana wind that's coming in is really going to be trapped. And so we see this happen a lot in the Los Angeles area. Okay, I think that's it for thermal inversions. If you have questions, we can talk more in class. Thanks.